to the Pravasi Bharatiya Divas Conference on Future of Natural Resources, Hydrocarbons, Rare Earth Metals, and Blue Economy. The conference is organized by Ministry of External Affairs and Ministry of Earth Sciences and is marked by the keynote inaugural address by Shri V. Muralidharanji, Honorable Minister of State for External Affairs. To start the inaugural session, I would like to invite Madam Manika Jain, Additional Secretary, Overseas Indian Affairs, to make the opening remarks. Ma'am, over to you.
Namaskar. Good afternoon, good evening to all in the Eastern Hemisphere, and good morning to all joining from Western Hemisphere. Honorable Minister Shri V. Muralidharanji, Secretaries from Ministry of External Affairs and Ministry of Earth Sciences, panelists and participants. Ministry of External Affairs does series of Pravasi Bharatiya Divas conferences on various sectors and regions as part of our engagement with the Indian diaspora abroad. Normally, these conferences are done every 2 years leading up to the PBD convention in January, the subsequent year. However, this year we are celebrating India's 75 years of independence, also Azadi Ka Amrit Mahotsav. Our engagement with the diaspora on various platforms, including the PBD conferences, is to specifically focus on India's achievements since independence, the diaspora's achievements, and also to engage the diaspora in the future development of India. I must add that we are very proud of the achievements of all Indians across the world. We see that the energy security is one of the major issues facing various countries in achieving their sustainable developmental goals. Also, the race for securing uninterrupted supply of energy and obtaining technologies of future are making middle to big-sized economies put in more resources in research and innovation. Sustainable development, graduating towards green energy, and cooperating rather than competitive developmental models have become not only important but prerequisite for long-term existence of all of us. We in the Government of India think that the future of natural resources is a very important sector, not only for research but also for further development of humankind. Therefore, today's conference is very relevant and hopefully produce meaningful results. I'm grateful to the Ministry of Earth Sciences, who has actively collaborated with us to make this event possible. I also thank the panelists who are acclaimed names in scientific research and innovation from across the world. We have Indian overseas experts from US, Europe, and Australia today joining with us. What gives me great pride is that the members of Indian diaspora across the globe have been doing pioneering work in various fields, whether it may be business, economy, culture, social work, or scientific research. We have been collaborating in the fields of culture, community work, economy, and business with our diaspora actively. Now we would want the scientific community to come on board and work with us in finding answers to various problems and assist India in achieving greater strides in its development for the benefit of vast Indian population and humanity as a whole. Despite India's huge developmental challenges, the country is taking ambitious action on expanding green and renewable energy, energy efficiency, and biodiversity both on land and in water. Our concerns for climate change does not merely come from the realization of the adverse impact it has on developing countries like India, but also stems from the civilizational ethos of living in harmony with nature. Hence, India has set ambitious, nationally determined contribution goals for post-2020 period and is pursuing the target of 450 gigawatts of installed renewable energy capacity by 2030. India has set up various national missions for achieving its energy requirements in a very responsible and sustainable manner. The National Hydrogen Mission aims to make India a global hub for the production and export of green hydrogen. The Government of India has recently launched a multi-institutional program named Deep Ocean Mission, which aims at boosting scientific and technical innovations to advance marine research and exploration. The major thrust areas of this mission will include deep sea mineral exploration, technology development for sustainable mining of the potential resources, exploration and conservation of deep sea biodiversity, We see that the study for the future of natural resources is diverse, very exciting, and very challenging. This conference is one of the many steps taken to encourage the Indian overseas experts to collaborate in this journey. I hope that this conference will bring out interesting perspectives and give a direction to the future discourse on the subject. I thank you all once again for participating in this endeavor and hope that this dialogue will continue post this conference. I will now request Honorable Minister of State for External Affairs, Shri V. Muralidharanji, to share his views on the subject while delivering the inaugural address. He is joining us from a different city. Thank you.
Esteemed members of Indian diaspora, ladies and gentlemen, it's my pleasure to address you all today on the occasion of the first virtual conference on future of natural resources, organized jointly by Ministry of External Affairs and Ministry of Earth Sciences. Over 70% of the globe is covered by oceans, and about 95% of deep ocean still remains unexplored. Oceans are storehouse of food, energy, minerals, medicines, modulator of weather and climate, and underpin life on Earth. In fact, considering the importance of the oceans on sustainability, the United Nations has declared the decade, that is 2021 to 2030, as the decade of ocean science for sustainable development. Depleting land resources coupled with the ever-increasing demand for metals and minerals has led to the resurgence of global interest in exploring marine mineral resources. The Sustainable Development Goals, increasing population, transition to green technologies, etc., are bound to increase the demands for metals. Metals such as nickel, cobalt, and rare earth metals play a crucial role in promoting the renewable energy technologies needed to curtail global warming and the environmental and social costs often linked to existing terrestrial mining practices. Gas hydrate deposits may contain roughly twice the carbon contained in all reserves of coal, oil, and conventional natural gas combined, making them a potentially valuable energy resource. Hence, the development of marine mineral resources becomes imperative to meet the demand for future industrial and economic progress in a sustainable manner. India holds a unique maritime position. It is surrounded by the oceans on its three sides. Around 30% of India's population is living in coastal areas. Its 7,517 kilometer long coastline is home to 9 coastal states and 1,382 islands. For India, its oceans are a major economic factor, supporting fisheries and aquaculture, tourism, livelihoods, and blue trade. Minerals such as gas hydrates, polymetallic modules, polymetallic sulfides are abundant in Indian exclusive economic zone and Indian Ocean. Friends, India is one of the frontline nations in marine scientific research and is also actively engaged in exploring the resourceful ocean bed for meeting the country's future energy and metal demands. The Government of India's vision of New India by 2030 underlines the blue economy as one of the 10 core dimensions of growth. The blue economy, which consists of economic activities dependent on India's GDP. Prime Minister Modi ji envisions that India's energy independence is absolutely essential for its progress and for a self-reliant or Atmanirbhar India. He has emphasized the importance of blue economy for India's sustainable economic development and has resolved to make India energy dependent before the completion of 100 years of independence. India's accelerated progress in developing its blue economy and harnessing its ocean resources is an unalienable key to India's energy self-reliance. However, India is determined to reach this milestone in a sustainable and responsible manner. To achieve its climate goals, India has set target of 450 gigawatt of renewable energy by the end of this decade. That is 450 gigawatt by 2030. India has shown the way in collective initiative for tapping the solar energy. We believe in one sun, one world, and one grid. With respect to harnessing marine resources, the Government of India has taken several initiatives to explore ocean resources for sustainable use. India has been conducting detailed studies and explorations on deep sea minerals, such as for polymetallic nodules in the central Indian Ocean basin since 2002, and for polymetallic sulfides in parts of central and southwest Indian ridges since 2016. We are also conducting experiments on harnessing energy from ocean and have also taken several initiatives over the years for development of marine fisheries in sustainable manner. We are also carrying out offshore marine survey and exploration in the exclusive economic zone of India to identify potential zone for mineral resources. Further, we are undertaking scientific studies and development of technology for gas hydrates for the exploration of ocean resources in Bay of Bengal, with particular reference to two identified blocks in Krishna Godavari Basin and Mahanadi Basin. Progress made by our country in marine mineral exploration is commendable and at par with other nations involved in advanced marine exploration and research. However, the challenges faced by us include the development of suitable technologies for effective mining of some of the deep sea mineral resources and exploitation of gas hydrates resources. I hope that this conference will address some of these challenges. Post-pandemic geopolitical and economic trends offer an unprecedented opportunity for India to emerge as a rare earth supplier for the world. Rare earth elements are crucial to many strategic applications, including missile navigation and sensor systems. They are present in almost everything we use, from processors to advanced alloys to electric vehicles to consumer electronics and industrial machinery. India, with nearly 6.9 million tons, has one of the largest rare earths reserves, but they remain largely untapped. Deep sea mining may prove to be a sustainable source of rare earths for India in future, but require further technological innovation. This can be achieved by collaboration and cooperation of scientific community of both India and abroad. Friends, Indian diaspora is currently one of the largest in the world, with over 31 million people of Indian origin and non-resident Indians spread across the globe. The diaspora has achieved great success in different fields. People of Indian ethnicity can be witnessed at the forefront of politics, business, culture, and science. Today, we have eminent scientists and innovators, researchers and scholars among our diaspora who are making India proud of their achievements. The panelists of this conference are a few of them. I am sure that you all can be a catalyst in finding innovative and sustainable solutions to these challenges which are before us today. Our purpose of holding the conference on future of natural resources under the umbrella of PBD conferences was not only to connect with you, but to get your expert views on such an important issue. I may also take this opportunity to convey that we have been engaging with the diaspora at multiple fora to introduce a variety of initiatives and measures that aim to strengthen and support the diaspora's connect with India. Some such initiatives are celebration of Pravasi Bharatiya Divas, conferring of Pravasi Bharatiya Samman Awards, hosting various sectoral and regional PBD conferences, organizing No India program for youth, and Pravasi Tirtha Darshan Yojana for middle-aged and elderly. Our scholarship program for diaspora children gives opportunity to the diaspora children to study in Indian universities and institutions. The ministry also encourages our missions and gives grants for organizing cultural events with the Indian diaspora. Now our missions are enthusiastically engaged with the diaspora in organizing activities for celebrating Azadi Ka Amrit Mahotsav. Friends, in conclusion, I would like to wish all the panelists and participants a very successful and productive deliberations in this conference. I am confident that these deliberations will be fruitful in bringing out some innovative recommendations for future action. Thank you all.
I thank Honorable Minister for his illuminating address and valuable insights. As the Minister had mentioned, India's phenomenal achievement regarding the initiative of the Global Solar Alliance is underpinned by an unwavering belief of one sun, one world, and one grid. India's progress in harnessing its natural resources, including those in the deep ocean, is the key to India becoming energy self-reliant in sustainable and responsible manner. On behalf of my ministry, I would like to express my gratitude to the Ministry of Earth Sciences for their continuous support for organizing this conference. I am also very grateful to Madam Manika Jain, Additional Secretary, Overseas Indian Affairs, for being the pivotal force in organizing this conference. I would like to especially thank Dr. Parvinder Maini, advisor and scientist from Ministry of Earth Sciences, for her valuable guidance. I also wish to thank our esteemed panelist members who have joined us today from different time zones to make this event a success. I wish to take this opportunity to welcome and thank all the diaspora members and our missions who have joined the conference online from different parts of the world, and everyone else who is watching this conference live from MEA YouTube channel. We are now going to start the technical session. We have with us a very diverse panel of 7 eminent scientists from around the globe, from Australia, France, Germany, Norway, UK, USA, and India. The panel discussion will be moderated by Dr. T. Srinivas Kumar, Director, Indian National Center for Ocean Information Services. I now invite Dr. Srinivas to kindly start the panel discussion.
Thank you very much, Ms. Ankita Mittal. Ms. Manika Jain, Additional Secretary, Overseas Indian Affairs. Shri V. Muralidharan, Honorable Minister of State for External Affairs, and all the fellow panelists who are in this important event. I would like to welcome all of you on my behalf to this great event which is being organized by the MEA and MOES on future of natural resources. I'll be the moderator, and I was introduced by Anika. I'm the director of the Indian National Center for Ocean Information Services, which is an autonomous institution under the Ministry of Earth Sciences. So we have 7 distinguished panelists, all representing the Indian diaspora, working far and wide all over the world, working on marine living and non-living resources, who will be contributing to the panel discussions today. We have a wide range of experts dealing with polymetallic nodules, hydrothermal sulfides, gas hydrates, exploration, mining, technologies, environmental impact assessments, and so on and so forth. We hope to hear from you and then learn from your rich experiences and see where our institutes in India can work with you and connect with you in taking this mission forward. So a bit of logistics before we move on to the actual session. So we have approximately about 75 minutes of time. We have 7 speakers who will be making brief presentations of 10 minutes each. So that will leave us with about 5 to 10 minutes of discussions. So we'll keep the question and answers to the end of the session. I would invite each panelist introduce you briefly and then request you to make your presentation. So I will give you a hint when you are at 9 minutes so that you will have a chance to wrap up in another minute. And for the audience who are out there, please type your questions in the chat box, address it to the moderator. So my name is listed there, Srinivas Kumar. If you type in the questions and address it to me, I will actually compile all the questions, and then please let us have these questions, and I will ask the panelists to answer them at the end of the session. So with that logistics sorted, I would like to invite the first panelist, Dr. Seshi Nair. Seshi Nair is a plankton biologist. He is affiliated to the South Australian Research and Development Institute. Seshi has been working for more than a decade on applied industry-focused research programs on in the algal production group. He has over 25 years of experience researching on mangroves, coral reefs, estuarine reefs, seagrass meadows, and so on and so forth on all the coastal and marine ecosystems. And earlier this year, Seshi was awarded a 1.5 million economic and business growth fund by the South Australian government, matched by 3 million from the industry to develop seaweeds in South Australia. Over to you, Seshi. You can share your presentation and start your talk.
May I know if you're able to see the presentation?
It's still coming up, so yes, you can put it in full screen if you can, Seshi.
Thank you. Okay. Good evening all, or good morning and good afternoon from different time zones. Honorable Minister, the organizing committee, fellow panelists and participants. Thank you to the organizing committee for giving me this opportunity to present to you from Australia. I'm located in Adelaide, the capital city of South Australia, when it's about 10 p.m. at night. I'll be talking about a subject which is very similar or draws a lot of parallels between Australia and India. And that's about cultivated seaweeds in unlocking the blue economy of India. Australia and India are on a similar path with regards to the seaweed industry. It's very early days, and we have a long way to go before we can make it into a commercial reality. So if you look at the FAO numbers, there's about 35 million tons, round about 35 million tons of biomass was produced in 2019. On the brighter side, about 97% of that is coming from the cultivated. It's sustainably cultivated, and only 2% of it is from wild harvest. So that is a very good sign, and we have to ensure that that increases further and we rely on more cultivated biomass rather than wild harvest. Asia accounts for about 97% of the global seaweed production. And the global trade in seaweeds currently stands or sits at about US 2.65 billion. If you look at India's share in the global seaweed production, it is a minuscule 0.01 to 0.02%. And Australia is also in the same boat. It's exactly about 0.01%. So there are, as I said, there are a lot of parallels between the two nations. And through this presentation, what I was hoping to do is to bring in my expertise in working with other countries like New Zealand or the Philippines or Indonesia, where seaweed industry is quite big, and bring those parallels into the current scenario. So the current market value for the Indian seaweed is about 33 million US dollars. And that is only a small amount. I mean, there is a very big opportunity or a significant opportunity to expand this and make this industry significant. What are our competitive edges? If you look at the competitive edge for India, it's a vast coastline of about 8,000 kilometers. As the minister alluded, we have an exclusive economic zone of about 2.172 million square kilometers. From a seaweed perspective, there's about 844 species, out of which 30 are potentially commercially relevant. And this is in contrast to about 10,000 known species of seaweed species around the world. And South Australia is a hotspot with about 5,300 species, next to Japan in terms of the global hotspot diversity for seaweeds. If you look at the recent TFAC report, which was published in 2018, there is a potential to generate employment for up to 15 people on a per hectare basis. Very recently, there was a significant Government of India investment into the seaweed sector amounting to approximately $86.8 million US dollars. The farming potential, if you look at it, the farming potential, if you look at it, the TFAC reports points out an aspirational target. If you look at the territorial waters of India, there is a potential to farm 1 million hectares of water space with seaweeds. The estimated production from that space is approximately 500 million tons per year. And that equates to about 50 million tons on dry weight basis. Keeping in mind, that's about 13 times the current global production, which would place India on the top spot, probably de-seating Indonesia, Philippines, and China on the top spot where they sit currently. What are the potential outcomes from that biomass generation? There's an opportunity to provide employment to about 15 million people in the production and allied industries. There is a significant nutrient assimilation and potential, and with the recent nutrient and carbon trading credits kicking in, there's an opportunity to generate revenue of about US 3.34 billion just by selling carbon credits. Or nitrogen, which is even more because the nitrogen constrained industries are significant. It's about the revenue stream could be around the 15 to 75 billion mark, depending on what the pricing is. Phosphorus is a small amount, but it is still worth reporting, about 0.4 billion. And if you look at the market value of the biomass, it is $40 billion. Now, that is on the basis that it's $80 a ton, which is not much. It's only $8 a kilogram. That is where the opportunity to value add comes in and where India needs to cash in on that opportunity, either through biorefinery approaches or through other approaches. This is just a snapshot to show what are the various opportunities in the seaweed value chain. If you look at the seaweed industry, I mean, effectively, seaweeds are used in everyday products, from toothpaste when we wake up in the morning, to wine, to snack products, and a whole raft of other things. Whether we realize it is there or not is a different matter. Even the agar or the jelly that we consume has got seaweeds in it. So it can range from, if you look at fine chemicals and natural pigments, a project that I'm currently working on is to produce color pigments from seaweeds for the plant-based food industry. That's about $1,000 per kilo of the pure pigments. So the opportunities are endless, and India has a real great opportunity with the biomass that it is going to produce. Now, the future directions to develop this industry. There are a lot of things that we need to consider. Now, Philippines and Indonesia are very well established with the Capaficus and the Eucheuma industries. They have moved away from wild stocks. India is very heavily reliant on wild stocks. So what they have done is they have developed hatchery technology, tissue culture technology, and that's a very interesting way to tackle the need for inoculum for at sea or land-based cultivation. There's an urgent need to preserve the genetic gene pool or the endemic gene pool from our seaweeds. What we are seeing is a very big reduction in the wild capture or wild harvest of seaweeds, and that is a worrying sign for India. Development of family lines with climate change, the talk about disease resistance, and everything else in the that nature throws at us. We have to develop family lines or selective breeding techniques to develop genetic strains that have a good vigor. Functional genomic research for targeted metabolite synthesis. There's a lot of learnings from the terrestrial plant sector that could be adopted to the seaweed industry. Coastal subsistence farmers. Philippines and Indonesia are a good example where the government has stepped in, and all they provide these farmers who have been very reliant on the prawn farming sector, which has collapsed, was to provide them with a few Coke bottles, monofilament lines, and about 50 fragments of tissue cultured Capaficus or Eucheuma, and they set them off. And they're able to provide a daily bread to the family just by selling the seaweed that is cultivated in the marked areas. Value addition. We should stop thinking about it as a commodity-driven exercise. We have to start thinking about value addition, and for the very reason that I mentioned earlier in my previous slide. Now, with this comes a lot of policy and regulatory frameworks across the value chain to make sure that the industry development is seamless. And Australia is in the very same path. We are still learning a lot of things, and we have also got a long way to go with our industry here. Now, cooperatives are the best way to do it. I'm seeing more and more established in Australia at the moment with the tuna industry, which is at the brink of collapse. And the same in India has been in the forefront with cooperatives for a very long time. So it is a very cross-adaptable platform. Spatial mapping of at-sea and land-based cultivation zones and allocation of more aquaculture leases is very critical. And again, India is at the forefront in terms of spatial mapping, whether using remote sensing techniques or finer scale mapping systems. Screening of novel taxa. I mentioned there were about 880 odd species that occur in the Indian waters. I don't think most of them have been screened. So this is where the big challenge lies. Australia has got 5,300 species. We have probably screened about 10 or 15 taxa. So we've also got a long way to go. So there's a lot of parallels between the two countries. And the most important thing is the collaborative applied large government funded R&D programs, very similar to that $86 million that the government recently funded. But the key thing is to bring big institutions, the major stakeholders like CMFRI, NIOT, CSMCRI, MPDA, MFDB, and industry, the farming groups, the state and federal government departments, and university, adopting very similar to the model that has been adopted in European Union very successfully. And we have been canvassing the same thing in Australia too, because this is what is going to synthesize, or this is what is going to result in good collaboration for the benefit of the nation. This is just a snapshot of what an industrial scale farming looks like. The slide that you see, the photo that you see on the far left-hand side is an industrial scale production in China. China is one of the among the three largest global seaweed producers, and they also have land-based systems. And India has got an immense potential to develop this industry. And with that, I end my talk, and I'll be happy to take any questions later down the track. Thank you.
Thank you very much, Sashi. Thanks for that wonderful talk on the potential of seaweed culture, and thanks also for keeping time. And we'll keep the questions to the last. So if there are questions, please put them to me in the chat. And we'll now move to the next presentation by Professor Satish Singh. Satish is he's affiliated to the Laboratoire de Geosciences Marine, IPG Paris. He holds a PhD in theoretical seismology from University of Toronto, Canada. He has been co-author of more than 185 publications in international journals and 14 in Nature and Science journals, very high impact factor journals. Closer to home, he's on the research advisory committee of the NCPOR of the Ministry of Earth Sciences. He has been a leader of several marine expeditions. He's been a chief scientist. I now request Professor Satish Singh to give his presentation. Over to you, Satish.
Thank you very much. Can you hear me?
Yes, loud and clear.
Okay. Thanks for inviting me. It's my pleasure to be with you. And my talk will be slightly different than what we heard today. I've been working with India over the last 30, 40 years now. I am Indian still. So what I'm going to tell you that what has not been done in India and how to improve things in India. Mainly we'll focus on marine natural resources, which is my expertise. And it's a link with basic science because it's very easy to get caught into very focused industry-oriented problems. And you will see today, and I will try to point out that to do that, you need the fundamental science linked to industry. So my view is that the basic research is fundamental for any economic development. And in our area, in our sciences, through exploration and exploitation of natural resources, which we are going to talk. And I will do this through examples. We talked about gas hydrates. As you know that India has vast resources of gas hydrate, and India has been working on it for the last 30 years or so on this project. And you could find them on the continental margin, both on the east coast and west coast, and dominantly in the Andaman Sea. Your other motivation is mineral resources along. They are mainly produced either through the ridge axis or volcanism. I'll show you some of the examples why the basic research is essential for exploration purpose. And obviously, energy is the key area of research in India and all over the place. We are having COP26, how to reduce the greenhouse. The gases and oil and gas will remain in the future important source of energy. So I'll talk about all the three of them. So just to kind of point out, and I'm sure Kamesh Raju will talk about what's happening at the Central Indian Race, and some of the colleagues will talk about gas hydrates. So I will touch on these three issues and just to throw what needs to be done and how to advance, in my view. Here an example of the work I did on gas hydrate. That was in early 90s. As you know, gas hydrates are mainly formed by the methane and water molecules at high pressure and low temperatures. And they are in seismic data set. This is a Cascadia margin offshore Canada. And we are in early 1992 here. And at that time, you are very early stage of gas hydrate. This is the seismic reflection data set here you are seeing, which is the seafloor on the top. And you see the BSR, which is the bottom simulated reflector, which at that time was treated as it could be either a very large amount of hydrates, gas hydrates, could be a small amount of gas, or could be combination of hydrates, which contain about 64 molecules of the gas and the gas. So while at that time, we were not drilling at that time. We were very concerned that the gas will be released from the hydrate and the drill hole will collapse. And so we decided to do some advanced analysis of the data set before drilling using the techniques we developed early on. And here is the velocity structure as a function of depth. And the thin line is what they found when they drilled. And the thick line is what we predicted using seismic data set. The purpose and the paper was published in Science. It was a big discovery. What I'm trying to say that at that time, we were not interested in exploring gas hydrate. We are just trying to understand. India has spent over the last 25, 30 years on trying to do that. But I'm critical because we have not really made a big advancement. So I think what I'm trying to say that go back to the basics and think of the science problem and then go to exploration. So that's what gas hydrate. Second problem, we talk about minerals. Where do we get the mineral from? Minerals are formed from the magma coming from the deep earth. And magma comes in the crust, stays in the crust, and some of them comes to the surface. On the surface, when the melt comes, it forms the black smokers, and that's what your sulfide comes in. So there are a lot of minerals you are interested in are in these sulfide deposits which come from deep earth, and through the interaction between the water and the hot rock, which is the temperature at the 1250 degrees centigrade. So in order to predict where it is, what to make out of it, you had to do the basic research. And this research I did in 1998. We published in Nature, where we saw that this is the magma chamber, This is the magma chamber we see here. I call it melt lens. You have faults, you see them, which are bringing the water to the surface. And these magma chambers are linked to the hydrothermal circulation on the seafloor. So the message here is that if you talk about the France, Germany, US are doing research in mining on the seafloor because they have a very active research program on understanding the processes which brings out the minerals. Once you know where they are, what are the types, then you can go and explore. You can't just say that I'm going to explore tomorrow because this is our plan. And that's what I have seen here happening. Same for the gas hydrate, same for the mineral resources. So coming back to the basics, we need the link between the magma chamber and whole study together. Then coming back to oil and gas exploration, which we have been doing for the last 70, 80 years in India. And ONGC has been the key player in the whole area. And one thing, again, comes back to, you just go and look for oil and gas. You need to know what is the history of these structures. For example, continental margin of India. Do we know what is the evolution? What is the thermal structures? To produce oil, you need to cook the sediments. To cook the sediments, you need what was the temperature at the time cooking took place. So, for example, in India, some research has come out. We have not done understanding of the margin. For example, we do not know what is the crustal thickness around this area on the margin. How wide is the ocean continental transition zones? All these are essential for oil and gas exploration, which had been missing. I'll come back at the end of the day. All the countries, other Western countries, France, UK, Germany, US, Canada, all of them had a big program of continental margin. The reason was simply oil and gas exploration. However, I've been trying to tell this for the last 20 years. Nothing had been happening. So other area which is very interesting for India, that India has a spreading center between in Andaman Sea, between the Andaman Islands and the Malaysian Islands. There they have a spreading center. Spreading center, this is the work I did several years ago with some of my colleagues. There we also have magma chamber, and that magma chamber, which produces the minerals coming from deep earth, interacts with the sediments. When they interact with the sediments, they produce gold and copper and a lot of other interesting things which we do not know. So the message what I'm trying to pass here is that these are the data collected by a company which gave it to me a long time ago. However, India has not done much in this area. So my recommendation will be, the third point is technical developments. Again, we are very good at mathematics, very good at computing. And even with ONGC as a giant company, we have not developed a new way to, what I have done here, you have seen is by using new technology, new methods, we can do much better both for exploration, exploitation, and monitoring. And I tried to convince colleagues in India 20 years ago now to create companies because we are so good at math and computing. And country like Israel, which is a very small country, they have developed many technology, a company, small company, which are selling to ONGC and everyone else. So I think my message is not just that we kind of glorify what we do, trying to build up industry in India, which will help us to do the exploration and the mining. So to me, what I will recommend, if you're asking me, I've been asking this for a long time to start national program on the margins. As I said, all the countries have done it except India, which is needed to, by doing seismic study of the margins, refraction, thermal study, which will help us to exploit and explore the minerals, the energy resources we have around the margin of India. Similar program should be done for the ridge axis. If you're looking for minerals, you need to know where they come from. Again, for the last 20, 30 years, all the countries, US, UK, France have done it. We have not done it. And obviously, you need more young people studying these resources. And so my conclusion here is that Just don't go for exploration, exploitation. Think about the basic science, which will help you to build the basic exploration program. With that, I would like to thank you for giving this opportunity, and I'm happy to discuss anything you like later on during the discussion.
Thank you very much, Professor Satish Singh, for highlighting some of those basic science that we need to really address hand in hand with going for exploration and exploitation. And that's a very important point that you make, having programs on margins and ridges. So we'll come back to those discussions at the end of the session. Thanks also for keeping time, and let's now move on to the next distinguished panelist, Dr. Ravel Singh. Ravel is affiliated to the CSIR, Indian Institute of Integrative Medicine, and with the Senckenberg am Meer DZ Germany. Ravel is a marine ecologist specialized in benthic ecology and biodiversity. He specializes in microfauna, documents their role in ecosystem processes such as biogeochemical cycling and food web flows. He has been involved in several Southern Ocean and regional and global assessments on the anthropogenic and climate change impacts on marine ecosystems. Over to you, Ravel.
Hello, sir. Are my slides are visible? Am I visible, audible?
Yes, your slides are visible. They are, I think, in presenter mode. If you can put them in full screen, that would be much better. If you're having problems with that, that's fine. Please go ahead. Yeah, perfect.
Is that okay?
Perfect. Go ahead.
Thank you, sir. First of all, I think it's a great honor for me to be part of among that such a distinguished panelist. I think the youngest one. I finished my PhD in 2016. And after that, I joined as a scientist. I'm working with the Germans. And it's a great honor for me. I would like to thank the ministry for organizing this workshop, this conference, because I feel that it is a great opportunity for all of us to contribute in whatever the expertise we can. As the conference is about the marine natural resources which are lying in the ocean. And another thing is that how sustainably use these resources for the well-being of the humankind and the economic growth. I am a marine biologist basically, and I work on Benthic Fauna. These are the organisms which actually lying in the bottom of the zone. And I think with the mining or the exploitation of these mineral resources goes, as a scientist, it is our duty to also address the ocean ecosystem health, ocean ecosystem biodiversity, and that's what I think. Today's talk, I will give whatever the work I have contributed till now, and what I'm doing till now in the deep sea, and how it can be helpful for the technology people, as Professor Satish sir has said, the technology development. So how the technology can be developed with the minimum harm to the fauna which is living there. So I will skip this slide because it is already said about me. But I've been a part of these expeditions, especially with the Disco revisited area after 25 years. I would like to particularly highlight this. And there we actually assessed the disturbance which has been artificial mining, which has been done in 1990, and we revisited it again in 2015 during my PhD days, and I was a part of that in that group as a benthologist. Deep sea mineral resources. As I said in the first slide, that we have ocean. In the ocean, we have particularly these, the resources, natural resources, from hydrocarbon to petroleum to oil. And there are mineral resources which are actually 3 types of mineral resources, but particularly I will highlight the polymetallic nodules because I have worked on that. And these are the rock applications, and we all know, and they are important because they contains the elements which are actually needed for the present use of our daily beings. And they are distributed from the Indian Ocean, the Central Indian Ocean, to the CCJ in the Pacific Ocean, to the south in the Caribbean Basin. So somehow to mine these resources, it would definitely help to the mankind because of the modern system which we are living. Well, there is a International Seabed Authority, which is actually the body which regulates and manages these resources, and also fairly use these resources by all the countries, and India is actually participating in that. ISA has recently, they have issued the contracts of the exploration to the country, and India is a sole partner in the Indian Ocean for the exploration purpose. And with this regard, this mining technology, if I would say this, it is going on now. There are techniques which are actually testing up, but as a biologist, as a biodiversity scientist, it is definitely going to harm. It is definitely going to affect the benthic habitat there. And it is, as a scientist, it is it's a responsibility to generate the knowledge so that the mining company or the exploration people has an opportunity to develop the equipment like that so that the harm should be minimum. Recently, I was going through that and I saw that now many of these groups have started testing these mining equipment. Recently, the Global Seed Mineral Resource, the Belgium-based company, has tested the equipment. One of my colleagues was part of that expedition, and probably, it goes well, and probably in next coming years they are going to launch it. Similarly, the others as well. India is also trying with that. They're also building the machines to do that. But having said that, as I told you, that they are definitely going to harm, and harm especially, particularly the fauna which is living in the bottom of the ocean. Now, what is that fauna? It's called Benthic Fauna. These are the organisms which are actually divided from the macro, mega, which some organisms you can see, some organisms you cannot see, some of the microscopic, and some lives inside the sediment, some lives on the top of sediment, and they are important, definitely, in the oceanic point of view. They are important in the functional reworking of the sediment, and if I put another way, as a bio irrigation and bioturbation. They're also a food for the fishery, the demersal fishery, and also play a major role in the nutrient cycling. So there is a balance out there, down there, and it has to be monitored properly and studied properly. In Indian Ocean or in the general mining regions which are in the radar of this exploitation, there was some of the questions which were framed by me, by myself, that how I can contribute in this. Well, the first thought comes in mind that how many species are living there? Is there any specific fauna which is living inside the nodule? Is there a restriction of the species? Are there species which are endangered? Or is there any genetic exchange between the populations? And mostly to how the Indian Ocean, how the deep sea Indian Ocean or deep Indian Ocean has a benthic biological knowledge. So what we found that it corresponds very well with the other regions, with the other deep sea regions. Most of the species which are lying in the Indian region Indian Ocean. It is also, we can find in the Pacific Ocean. They are almost the same. However, the density, the numbers of these organisms were very less in Indian Ocean, in the deep Indian Ocean, and that we figured out after that. This is what the Professor Satish Singh was talking about, the technology development. We found that later on these box corers which we use, actually these box corers, when we lift it up, it releases lots of water and mud, and we lose so many organisms. So that is why we need to use this multi-corer recent technology. And another question which was very interesting, and it can contribute, or it can, in a way that I found out that whether these are organisms which are living in the nodule regions, are they similar which are living in the nodule-free region, the nodule-free abyss, where no nodules are there. So what I did is that some of the study is by my own, and some of the data I extracted from the other authors. And then what I did is that I compared it after comparing, what we found that the nodule region, actually, the region which have nodules, they have a high diversity, they have a high organism, they have a high accumulation of the benthic fauna. And now this was because probably this nodule bearing region is kind of habitat. Maybe the nodules itself is habitat for some of our species, some of the organisms living there. So after, when you do the statistical analysis, it gives you a lot of knowledge that the nodule-bearing areas has a different kind of fauna as compared to nodule-free regions. The next, I would say the next discovery, I would say, put away that whether these nodule curvaceae has some specific species, whether it also favors some fauna there. Well, yes, this is what I did from the Pacific Ocean claim. What we brought these nodules, we broken them, we sieved them, but we got that the nodule itself contains some of the species. These nodules is probably kind of habitat of some species. However, at a low level, or I would say at a higher, resolution level, species level, there are some species which are actually favoring the nodule as a habitat. However, owing to the difficulty in going back again to deep sea, this still is in the progress, which I really would like to carry on here. That whether nodules itself has some specific fauna which is not there in the other sediment. With this, mining test, I got involved in this, the biological response. I mean, all those experiments has been carried out, artificial mining experiment, which has been carried out in the late 80s, 90s, and after 2000 in India, index experiment, which was Dr. Ingole was a part of that. And what we did that is we simulated with this meta-analysis I have done, and we also found with this as well that the recovery of the fauna is very less. The tracks which were disturbed during that time, the recovery of the fauna is very, very less. So it have a long-term effect on the benthic community over there. Similarly,
sorry to interrupt, Ravel. Can you please sum up in a minute, please?
Okay. Yeah, I'll go that. I'll skip this. So now coming to the Indian Ocean mission, I'll directly go there. So Indian Ocean mission, I think these objectives, which are major highlights for me, would be the bioprospection of the deep sea fauna and flora, which is living there. This fauna, which we can use for the drug isolation or for the medicinal point of view. I think this could be a great invention for Indian point of view. And another aspect which I really would like to highlight, the technology. Yes, the technology we need for the deep sea mission to carry on that, and a wonderful technology that point of view. I mean, that there we can see the fauna down there. We can observe the fauna. We can extract as much as the information we have. And with this thought, I have recently involved in machine learning approach. I developed a software, and this software helps us to identify the organism automatically. We don't need to, go through a lot of process of seeding, sorting, and understand microscopes. So we have a software now. It will automatically distribute the organism just to put it on microscope under the microscope. So I'm also doing in the recent time. I'm also involved in the extraction of the information from the images itself to extract the biomass and biovolume kind of features, and this will generate a lot of information and a lot of value to the Indian deep sea mission point of view. And on this note, as the time is concerned, I would like to thank. It's a great opportunity for me. Is there any question, please? Happy to answer that.
Thank you very much, Ravel, for that very interesting presentation on what would be the impact of mining on benthic fauna and the automatic identification of benthic fauna is also something which our audience will find certainly interesting. We'll come back to the questions, but thank you very much. We'll move on to Dr. Shamchand, who is the senior research scientist in Geological Survey of Norway. Sham has a PhD in marine geophysics, and he works on development of technologies, methodologies for seismic waveform inversion. He works on gas hydrate modeling and interpretation. So over to you, Shyam. Please go ahead with your presentation. We can see your presentation already. Please go ahead.
Thank you. Thank you for inviting me for this conference. And I would like to thank Ms. Monica Jain, Mr. V. Muralidharan, Economic Minister for External Affairs, and distinguished panelists, and also the attendees from around the world. Just going into the topic of future of natural resources, I'm a senior researcher at Geological Survey of Norway, and I'm also associated with the Center for Arctic Gas Hydrate Environment and Climate, which is a center for excellence specifically made by Norwegian government to study gas hydrates. I will divide the topic into three major things to just go through these topics in a combination and also in different. Coming to gas hydrates, already Satish Singh has already given an introduction to gas hydrates, but just to briefly give an overview on it. Gas hydrates are basically made of methane, and it forms in high pressure and low temperatures when methane is present. It looks like ice, and you need to have methane to form gas hydrates, and then the methane is coming from microbial generation in the sediments, and also from maybe leaking from hydrocarbon reservoirs. This is a very very well known picture of gas hydrates. It can form in, for example, in deep frozen areas in the Arctic, and then in marine areas where shown as a blue color, can form under the sediments where the pressure and the temperature is very particular for the stability of gas hydrates. Here is some pictures which I took from USGS fact pages, where you can see that it almost looks like ice interpreted with the sediments. So these are the things which you call it as gas hydrates, and it contains the very pure form of carbon as methane compared to the normal oil and gas. This creates lower pollution if you use it for. And there is a mapping done worldwide by different countries, and you can see this. There has been a lot of activities going around the world, and you can see that the yellow dots represent the recovered hydrate. In the north, you can see where I'm sitting, in Norway. We have been doing a lot of work regarding gas hydrates in the last 12 to 15 years. After I joined, 12 years in the Geological Survey, and then before that also I was working in UK on a EU gas hydrate program where we initialized all these methods, and Satish knows very well about this program because he was involved in the initial startup of all this research in England itself. So there has been a lot of drilling going on in the last decade or so. You can see these yellow dots are all around the US coast, and then you can see a lot of yellow dots in the offshore Japan and China, and also these activities in offshore India. And also there has been gas hydrate present inferred from various methods offshore around the world. Here is another map which is showing what you call as a stability zone for gas hydrates. This is the depth below the sea floor where the gas hydrate can be stable. So if it is blue, 0, that means that areas you cannot find hydrate because the temperature is too high or the pressure is too low, maybe close to the coastal regions, for example. Then, and if you look at the Indian offshore, you can see that there's a large region with stability. But as I said in the beginning, you need methane to form hydrates. The stability is one factor, and you need the production of methane either from leaking from deeper soils or formation within the shallow sediments. So now coming to gas hydrate as a resource. We have been, or many countries have been thinking as it as a resource. So first thing comes to mind is to estimate the resource potential, whether it is actually, you can find hydrates here and there based on these conditions, which I mentioned just before, but you need a certain amount of hydrate to produce it if you compare the cost of production, and then you have to put this highly economically reasonably method to produce the hydrate from the ocean environment, and also you have to think about environmentally safe production because you are moving into an ocean environment compared to the coastal zone or the land where mainly the oil and gas production is going on, and also think about the the geological environment and climate, because now we are moving to a world where the climate is changing drastically, and all this is happening because of the input of CO2 in the atmosphere, and then that input also can be dangerous with the methane released into the atmosphere, because it's very, very highly affecting the atmosphere with compared to even CO2. So now coming to resource mapping, India, I have been a part of the initial mapping program of the gas hydrates in India, and I was initially a PhD student at NGRI and also a scientist there. So there has been, I was working together with late C. Subramaniam and S.I. Reddy and Hanumant Rao on these topics, and then we mapped, we had a map which is showing the potential zones, and this is like a gas stability map of India, which has been made. This is taken from USGS, but similar maps were made by NIO and GRI and others. And then, based on other factors, potential zones of gas hydrates were established. You can see the red small regions as highly prospective zones of gas hydrate. Then, based on this map, India went ahead with this drilling program where there was this two NGSP programs, one in earlier, then which was drilled in KG Basin, Mahanadi Basin, and Andaman offshore, and also later in NDP2, where also in the first phase there was a Kerala Konkan Basin drilling, and then drilling continued in NG02 at KG Basin and the Mahanadi Basin. So this has been already done in these areas. And the production potential is also depending on how much, as I mentioned earlier, how much gas can be released from gas hydrate. As I shown earlier, the gas hydrate sits within the sediments as a solid. You can release it by reduction of pressure or increasing the temperature, or use of some chemical agents to change the stability point. I'm happy to, I was attending many conferences, and I'm happy to see that ONGC actually participated in the initial phase of drilling for gas hydrate in the Alaska, Canada area, and they were being mentioned everywhere when this topic of hydrate drilling is coming up. And this is a picture from recent drilling in offshore China, where they showed the production of gas rate and elapsed over time, and then you can see there is some amount of production. I don't still know how much economical is to produce in this area. So that's a major factor which is driving whether we can produce gas hydrate from a gas hydrate reservoir or not. That still has to be established, because all these countries, whether it's Japan or US or Canada or China, all these countries were just experimenting on this factor, and that is still a factor which has to be established. So, but in Norway, it has gone in a different way. Norway already has a lot of hydrocarbon reservoirs with the oil and gas. We are exporting a lot of oil and gas directly through pipelines to England also. So gas hydrate is a kind of an extra thing we can be, if there is needed, we can extract. So it has been, talk about gas hydrate started late, but it has been done in a proper way. Like I'll say, what we established first was there is a CAGE center, which is a combination between Geological Survey of Norway, University of Tromsø, and established a center for excellence with the help from the Research Council of Norway, with a lot of funding and a lot of facilities. And what we do is a multidisciplinary study of environment. So as the speakers before mentioned, that's the biggest thing. We have to establish a technology. We have to establish what's the environment we are dealing with, what's the biology, what's the geology, and all these things before we go into what kind of drilling of gas hydrate, because we don't know. There are a lot of unknowns related to it. And there's also another program we start up along with that is what we call a Mariano program, which is a mapping of the offshore of Norway. We have been doing this for the last 12 years since I joined the Geological Survey. We have been mapping with the multi-beam. We have been taking samples all over offshore Norway. We have been looking at the biodiversity. We are looking at the oil leakage, gas leakage. We are looking at the landforms. We are doing all whatever possible of the seafloor and the water column and the currents and everything, so that we can establish what is the backline before we start anything. So this is also important when I talk about deep sea mining. So
sorry to interrupt, Shyam. Can you please sum up in a minute?
Yeah,
sorry
sure. So this topic has been covered by Satish and all. We have to monitor all the geology and environment. And when it comes to deep sea mining, for example, Norway has started in 2019. We mapped a lot of areas with a small stamp size, or it's not stamp size, like 10 square kilometer areas, to look at different things, different biodiversity in that area, and then we make maps of how it can be affected by changing different parameters, and then that's the basis for starting the mineral exploration in offshore. That's also being discussed here in Norway about how a blue economy can be established based on the knowledge and modeling, and then we go for mineral exploration. That is now starting up in Norway. That's so summarize. What I mentioned earlier was that we have to do the background study on environmental. We have to do the background study for environmental variables in the marine exploration, and also then only we can have a sustainable and well-planned blue economy. This is very important, as mentioned by previous presenters also. So thank you for your attention. You can find me in by searching either for CAGE or the Geologic Survey of Norway, and most of my publications are more technical, so I don't want to bring it here. Just if you have any question, please come back to me. Thank you.
Thank you very much, Shyam, for that very nice presentation, and then driving home the point that environmental assessments are very important. And then before we, when we move ahead with, exploitation, exploration, etc. Thank you very much. Let's move over to the next distinguished speaker, Dr. Prashant Jadawar. Prashant is a lecturer in petroleum engineering in the University of Aberdeen, and he's an expert who has been working on several key areas such as enhanced gas recovery, carbon dioxide sequestration and storage in natural gas hydrate reservoirs, and he's working on enhanced oil recovery and several such exciting areas. Over to you, Prashant.
Thank you, Srinivas Kumar. I would like to take this opportunity to thank Honorable Minister Muralidharan, organizers, and my fellow colleagues and panelists here for this opportunity to talk about natural gas hydrates. I will briefly cover challenges and what are the opportunities for Indian subcontinent. So my presentation will be a bit more technical. So I hope you will bear with me, and I will take questions in the question and answer session. I have more than 17 years of experience in working in academia and petroleum industry in UK, Germany, Australia, and India. As Srinivas has already mentioned, I have expertise in natural gas hydrates exploitation from porous media, CO2 transport, sequestration, storage, and enhanced oil and gas recovery. Currently, I'm about to launch a few projects on hydrogen and CO2 transportation and storage in depleted reservoirs and aquifers in UKC's region. Currently working on hydrogen production and transport injection in subsurface geological storage in porous media and its seasonal reutilization with Malaysian University, and currently my active research group is working on various topics. Let me go through very briefly. Gas hydrates are formed from gas molecules that are trapped within the cage-like water crystalline structure. They form at the high pressure and low temperature conditions, and those conditions can be seen on this diagram. Enormous volumes of one volume of gas hydrate can contain 164 volume of gas, and mainly methane in this case. And with such a huge quantity that is estimated about 1,000 to 1894 trillion cubic feet that could exist total in Indian subcontinent along the continental margins. So it is huge potential worldwide. What I see is the production trials or tests have been carried out in deep water in Nankai Trough in Japan. It is mainly based on depressurization. Again, the China conducted, it is again based on depressurization technique. In permafrost, Malik well has conducted first thermal production test and then followed by depressurization later on. Of course, the China also conducted some tests in Tibetan Plateau, and the USA in Ignis Sukhumi field, where they injected CO2 for methane replacement and the production of methane subsequently. India, we are about to embark Natural Gas Hydrate Program 3, and which is something I would like to be very, I would be very keen to participate. Now, in terms of India's potential, I mean, Natural Gas Hydrate Program first identified natural gas hydrates in KG Basin, Godavari, and Mahanadi and Andaman Islands, found to be existing in fractured and clay-dominated reservoir sections, whereas the NGHP2 identified two areas, B and C, where these sites would contain natural gas hydrates, methane hydrates in sand reservoirs, and hence this testing is proposed in the NGHP3, and total amount that could contain that would be resources of natural gas hydrate is about 133 trillion cubic feet in this KG Basin area. And if we even recover 10% of it, we could be self-energy dependent. Self-independency would be achieved. So there are some challenges, however, producing those gas hydrates from India's continental margins. Reason being that both the KG basins, as depicted in this picture, in this figure, KG basin, hydrate reservoirs are located at really depth of 9,300 feet, which is more than double of the Nankan Trough gas hydrate deposits. Now, both of these are nearly very deep, so there could be challenges, and hence technological development is necessary in those regions. With regards to its production, this is some production well. Through the completions, what we really know is once gas hydrate is dissociated, it will have huge water production. So water production management is one of the key concerns. Secondly, gas will produce, but at the same time, it will carry water will carry some fine-grained sediments, and that could block the completion pores, etc. Moreover, the permeability of these sediments is very low. So all these problems are not new to oil and gas industry. Hence, the technology that is already existing in oil and gas industry could be applicable in these gas hydrate reservoirs. And of course, the location distance to market is very key in the exploitation of natural gas hydrate reservoirs in India's KG basins primarily. One of the key concern is availability of data for performance prediction of how the natural gas hydrate, if we go for full production, how it will behave in terms of production rates, geomechanical stability, in terms of geologic and geophysics data, which is available to some extent now. So these are the concerns with the and challenges with the hydrate production. What we and I proposed back in 2004, and we injected CO2 into a micro model at pore scale, and followed after the one chemical which is kinetic inhibitor or anti-agglomerant, and that delayed the hydrate formation, allowed CO2 to interact with methane, and that produced methane bubble. We can see here, so methane recovery is possible. And we also shown in the laboratory that sediment stability, that is a main concern for gas hydrate production, is also taken care of by CO2 methane replacement in gas hydrate. So what we see in this picture, the gas hydrate structure, which is somehow distorted in 90 minutes after CO2 flooding, due to this CO2 methane exchange, it has regained shape after 163 hours of production after CO2 injection. So this also takes care of sediment stability. In terms of field trial, Ignis Sukhumi test in North Slope, Alaska, CO2 was injected, and about 48 million standard cubic feet of CO2 remained in the reservoir, nearly half of the injected. And this shows also good potential for CO2 methane replacement and CO2 sequestration, as we are mostly talking about decarbonization of the economy and net zero circular economy. Yes, this process can be combined with inhibitor injection as well as depressurization, which is standard method of hydrate production. Now, coming to the area of KG Basin B and C, where we need to identify whether the CO2 sources are available. And I can see from this map obtained from Vishal et al., who published paper this year, about 2.5 to 5 million tons of gigatons of CO2 can be captured and sequestered per year in the region around this Visakhapatnam and the Kakinada. And in this coastal region, there is huge potential of carbon capture and then injection into the methane hydrate reservoirs. Now, once CO2 is produced, there is also network available for methane is produced from the CO2 injection. Produced methane can be transported to and connected to Pan-India National Grid pipeline, which is planned, and it is about more than 33,000 kilometers. And the infrastructure is already there. Reliance is producing for about 1,500 meters, depth of 1,500 meters from KG D6 reservoir. And I think there is a good potential for application of technology and other scientific knowledge there. What I'm proposing,
Prashant, can you please sum up in a minute?
Yeah, just a couple of slides. So what I'm proposing is to develop industrial clusters. I mean, those industrial clusters are very good examples of developing industries around developing, creating huge amount of jobs, tens of thousands of jobs. Last week, UK government approved billions of pound project for developing such a cluster that is called East Coast Cluster. That connects Teesside facility and the Humber facility, and that is transporting CO2 for subsurface storage, and it's more than 100 to 145 kilometers in endurance. BP, Shell, Equinor, and big companies are involved in this project, and I think this is good way forward for exploitation of natural gas hydrate technology. What I'm to be fair, this is good way of also developing technologies for net zero emissions, carbon capture and subsurface storage, of course, CO2 as CO2 hydrates, bioenergy CCS, and also hydrogen-based electrification and natural grid integration. So there are few challenges with respect to that. There are completion technologies. Maybe we can utilize horizontal wells, completions, multilateral drilling, identify and assess various gas production on physical and mechanical properties of gas and reservoir systems. Different production models needs to be developed at micro and pore scale, and how we can upscale those models to this field scale. And the regulatory aspects, operational cost, taxation, climate change policies, development of partnerships is important, that I would stress on. And then the purpose-built gas hydrate drilling and production systems would be recommended for such natural gas hydrate production from the reservoirs. I think I will stop here. Here is my capability in my lab that I look forward to any collaboration in the future.
Thank you very much, Prashant, for highlighting those, very promising. You say that actually existing technology in the oil and natural gas industry can directly be adapted actually for gas hydrate production, exploitation and production. We'll come back to you with questions and connect with you. Can I actually ask Ms. Ankita? So we are running a bit behind time, so we might need 20 minutes more. We have 2 presentations to go. So can you please leave the meeting open 20 minutes, at least until 6:20 local time. So Ms. Ankita, please, so that we can continue on with the other presentations.
Sure, sir. Please go ahead with the presentations. We are all sitting here and watching you.
Thank you. Thank you very much. So let's move over to the next presenter, distinguished panelist, Dr. Hanmant Singh. Hanmant is a professor at the Northeastern University. He is a PhD from MIT and Woods Hole Oceanographic Institution Joint Program. His research area is in the field of robotics, imaging, mapping, and so his strong interest in UAVs, etc. Over to you, Professor Hanmant. Please go ahead. We can see your presentation. We can't hear you yet. Maybe you are muted. Can you please check your microphone? We can see your presentation though.
Let's try that again. Can you hear me now?
Yeah, we can hear you now. Yes, please go ahead.
I apologize. Okay, so what I thought I'd do is I'm not, as you said, I'm not a gas hydrates person, but what I am is a technologist, and I've worked a lot with science, in the last 25 years of my career. I'm going to start off by just showing you a little bit about some of the vehicles that I work with. There's Alvin, which is a manned submersible. It's rated. We've just done an upgrade on that at Woods Hole. It's rated to 6,500 meters. There's Jason, which is an ROV, and that's also rated to 6,000 meters. And then what I'm going to try and talk about a little bit more is an AUV called Seaweed, which I developed and along with my students. And we commercialized, and we've used it in a lot of interesting ways, which might be relevant to what's going on. And just to give you a sense of some of the things that we've been doing, even as a technologist, I've been to hydrothermal vent areas, like you can see in this video, and then I'm going to talk a little bit more about imaging and fisheries and polar work. So, when we first started out as a roboticist, we saw the need to build a new kind of robot, and the idea was to, when you look at Alvin, it costs close to $50 million. When we look at Jason, it's of the order of $10 million. And most AUVs are, $3 to $4 million, which is a very expensive way of going. And so our original thought was to build something a little less expensive, and also to use it for applications closer to the coastal ocean. We built this thing called Seaweed, and to make a long story short, they're now, right now, 15 years later, there are 12 of them all over the world. The Australians have one, which is part of the national facility. And the other picture you see is from Taiwan, and there's 5 or 6 of them being used by the U.S. government. In fact, the one on the right is used by NOAA, that I'm going to talk about a little bit. And the reason I'm talking about this is just to try and give you all a sense of how these things are made, how collaboration occurs. I'm not a fisheries biologist. We built this robot. I was at a conference similar to this one, and we talked about it. And a biologist, fisheries program manager came to me and said, can we try this robot for fisheries? And this was 2003. And this expedition, some of these pictures are taken from 2005, where we went out with them to prove that, or disprove that this vehicle could work for fisheries. And, long story short, first it worked. We did a 2-year program with them. They liked it so much, they wanted to extend that. Eventually, they bought their own vehicles. And now, 18 years later, they're using their vehicles, 3 to 4 months a year. And what's happened is we've gone, in this case, we've collected literally more than 1 million images associated with fisheries in the Northwest. And we've slowly gone from building these robots, which allowed us to collect a lot of data, to now analyzing the data using machine learning techniques, so that we can actually go from data to information, and which is a really big thing that we should think about. The other aspect of this, now this was a small little collaboration, but over time it has wound up becoming something really big. And as others saw it, they also jumped on the bandwagon. And as I said, we now have a dozen of these vehicles all over the world. Here's another example that I want to highlight, where in the first example we had a technology and we could use it in very interesting ways. Now, this example that I'm going to highlight is a little more relevant to what I think about in terms of collaboration with India. In 2007, we went out to the Arctic, and since then, I've done more than 20 expeditions to both the Arctic, the Antarctic, and Greenland. And here, the big difference is, even in the US, where we have a lot of funding devoted to science, it's very hard to go out and get icebreakers, not just from a cost standpoint, but also from the standpoint of opportunity cost. If there's only 40 days of icebreaker time available to the US community, if you get 30 days of that, that means the rest of the community did not get the 30 days that you got. So it's really important to be collaborative and make good, take good advantage of what you're doing. And the way to do that is really to, collaborate across borders. So these are just some of the expeditions. We've gone out with folks from Denmark. We've gone out with folks from the British Antarctic Survey. We've gone out with people from the Australian Antarctic Division. Of course, our primary funder was the National Science Foundation. But we've done all these expeditions, and we've also gone out with industry, the Oil Spill Research Institute. So, the whole idea here is to really exploit this collaborative atmosphere. And here's just a little video. This is, some of my students working on sea ice mapping with the Australian Antarctic Division. One of the other big issues that we want to talk about is the fact that we want to really involve our students so that we have this new generation that's ready to work with these problems as they show up. And one of the big issues I always think about is one of the big things I think about with students is when we started out having students, how many students can we really afford to bring into polar work? What are they going to do later in their lives? And that was my original thought. But nowadays, when I work at Northeastern, what happens is I get literally, I'm not making this number up, more than 500 students applying for robotics from India to come to our graduate program. And a lot of them will work on these interesting problems and then go on to work on autonomous cars, autonomous aircraft, and all these other things. So getting these students in, and some of them will stick with the problems that we really want to work on. And getting these students into our ecosystem is, I think, one of the really important things that we should do. And now, as I wind up my talk, there's a couple of other things that I want to point out. One of the really great successes of India has been our space program. And one of the things they're not afraid of is failure. Going out there, because we all know rockets fail. And the oceanographic science is very similar. We have a saying, the sea is not cruel, but it is unforgiving. And so, here's an example. We all talk about our successes, just like I have in the previous slides. But what we don't talk about is, and we should, is, when we lose a vehicle. And here I am in the Antarctic. The captain of this icebreaker is very unhappy because me and my crew were trying to find a robot which is stuck underneath there. And we actually, in this case, actually found it. But again, we should be prepared to lose equipment and expensive equipment. And that's an important point to make. Okay. And then, I'm going to just end this with some final thoughts. One is, whether it's methane hydrates, I think it's very important to work in that area. But I think we should also take the long view that, we are, as a country, we are the only country in the world that has an ocean named after it. Okay. And, and I mentioned that to lots of people and they all smile at me. And it's, and we also have the monsoons, which really affect most of the country, and they're coming from the ocean. But if I go to, one of the questions I had at a quiz show where we had some very good high school students is I asked them to, they can all point out where the Himalayas are, but nobody can point out where the 90-degree east ridge is in the Indian Ocean. Okay. And so we really need to make the people of India understand the importance of oceanography. Okay. And then, and I'm going from backwards. And then, of course, once we do that, we should exploit our strengths. We are doing so well in software, in data handling, in machine learning. And now we have these really nice projects going on at the high school level where people are really interested in robotics. Let's also start having them think about oceanography and instrumentation for that. And just like with the space sciences, no fear of failure. We will lose vehicles. Our technology will get lost on the bottom of the ocean. I will guarantee you that. We don't have, we have to do our level best to make sure that doesn't happen. But we should educate our sponsors about, what the relative risks are. We need to involve students. The more students we have, even if they, come into our discipline and slowly move to other disciplines, it's really important to get them in there because they are the people who will be the next generation. In 10 years, 15 years, almost everybody on this panel will have retired or will be thinking about retirement. But we want to bring that next generation up. And finally, we want to talk about collaborations. One of my biggest failings, I would say, is I have collaborated with, I've been on 60 expeditions all over the world. I have been to NIO, and I've, loved my interactions with scientists there. But I wish I could collaborate more with people from India. Okay, and it's not just about me. I think we should collaborate across disciplines. Science, engineering, technology. Physical oceanography, geology, biology, marine biology, and then also across international borders. Oceanography is so expensive that, it makes sense to include people just like you are at this conference from not just the diaspora, but the best scientists in the world, because, the Indian Ocean is one of the lesser studied oceans in the world. And I'm sure there are lots of people who would be very excited about working in this area. So I'm going to end it there. Thank you so much.
Thank you very much, Hanumant, for making those very important points: cross-disciplinary collaborations, bringing in students, working on things like ROVs and how we can use them in polar regions and so on. Thank you very much. You bring a very important and very different perspective to the discussion. Let's move on to our last panelist. Very important talk again by Dr. K. Kamesh Raju. Kamesh is a PhD in marine science, and then he has a lot of experience, 37 years of research experience in marine geophysics, tectonics, and geodynamics. He has been involved with the RIDGE program and worked on understanding of the ocean floor tectonics at the dynamic plate boundaries and so on. So over to you, Dr. Kamesh Raju. We can see your presentation. You can start. You seem to be muted. Dr. Raju, can you please switch on your microphone?
Okay, can you hear me now?
Yeah, please go ahead.
Okay. Honorable Minister, organizations, MEA and MOES, and distinguished panelists. First of all, thanks to MEA and MOES for giving me this opportunity to talk on this very important conference. Basically, I would like to give an overview of the entire gamut of marine non-living resources in the context of Indian context, covering from the beach resources, so the placer deposits, to the gas hydrates, to polymetallic nodules and the polymetallic sulfides. As Professor Satish Singh has rightly pointed out, all these resources, their occurrence, their origin, their occurrence, and their abundance and their potential are governed by the internal working of our planet, which is defined by the plate tectonics. So I absolutely agree with Professor Satish Singh. We have to tightly couple the basic science and exploration in order to harness these resources. So going ahead with this various resources that we have in the Indian coastline and the deep seas, we have the placer deposits on the shelf region, and then we also have the phosphorites on the checker again on the shelf region, and then of course we have oil and natural gas, and then the gas hydrates in the slope regions of the Indian continental margins, and we have the polymetallic nodules in the basal plains. And we also have a resource called cobalt crust, which deposit on the sea mounts. We have done detailed studies in the Afanasi nicotine sea mount to delineate this cobalt crust deposits, and we also have this polymetallic sulfides, which occur on the mid-ocean ridges, and the process was very well explained by the Professor Satish in the talk. So this is the placid deposit exploration that has been carried out, and we have found at least when this presentation actually has significant contributions from various teams working at different organizations across India. Major contributors being the CSIR NIO, Goa, and NIOT of MOES, NCPR of MOES, CSIR, NGRI, GSI, and others. So mainly placid deposits, rich reserves have been found on the coasts of Konkan coast, Kerala, Tamil Nadu, Andhra Pradesh, Orissa, and parts of West Bengal. Most of this work has been done by the CSIR, NIO, and the GSI. The various geophysical techniques have been used to delineate these deposits, and the exploitation or harnessing of the resources is at various stages of development. So coming to the gas hydrates, a lot has been spoken. So I don't want to go into the basics of the gas hydrates, but as has been told, these are the ice-like crystals embedded in the sediments, within the sediments, and these almost look like and contain methane and water molecules mainly. The results have been found in Krishna Godavari Basin, Mahanadi Basin, and the Kaveri Mannari Basin regions. Recently, we have discovered the coal seeps in the Krishna Godavari Basin at a depth of 1752 meters water depth. These coal seeps are emitting methane, which is actually very shallow occurring methane, which is emanating from the seafloor. It was imaged by the multi-beam bathymetry backscatter images. You can see it here. And we have the abundance of coal seep biota, which is surviving on the chemosynthesis. Interestingly, these biota are similar to the biota which we see on the hydrothermal vent systems, which are again hot vent plumes coming over there. So it's interesting to actually establish a link between the ecosystems to these extreme environments, which cold and hot environments. The studies have to be taken up. And this is the example from the Kaveri Mannari Basin. As Professor Satish Singh has told, these are the VSRs which were identified, which led to the further exploration of this region. Large areas of gas hydrate bearing zones have been delineated in this region, about 1,243 square kilometers, and 996 square kilometers are delineated in the Kaveri Mannari Basin. And there is a different type of chemosynthetic biota is discovered in this region. So coming to the other resource, for example, the major resource what we have found in the Central Indian Basin, the polymetallic nodules program. As India has got a lot of maritime heritage, and we have started early on in the 1980s, the nodule exploration. First nodule was discovered in 1981. Then on several investigations have been carried out. About 30,000 square kilometers of area has been mapped, and 11,000 seabed samples have been recovered from 72 expeditions, and extensive fieldwork has been carried out. And then based on these initial surveys, we have applied for the exploration rights to the International Seabed Authority, and then we have got allotted 150,000 square kilometers of pioneer area has been allotted. This is India is the first country to venture into this kind of deep sea mineral exploration in the Indian Ocean. And later on, in the recent years, we have conducted several studies. These studies also have resulted in more than 1,000 publications, which has actually enhanced our understanding about these resources and its potential as a and origin and the potential as a resource. And recent surveys have identified first generation mine site, and then we have actually conducted several environmental studies also and applied for the environmental clearance from the International Seabed Authority. This is the kind of application areas allotted by the International Seabed Authority. These blue boxes are belong to India. This is the polymetallic nodules region, and this is the polymetallic sulfides region. The other countries are also involved, like Germany, Korea, and China in the Indian Ocean. But we can say that we have the larger footprint in the Indian Ocean region in terms of exploration of the deep sea mineral resources. So these again the details of the resource estimates in the region. We have about 380 million metric tons of dry nodules are estimated in the region that is allocated to us. That's retained by us. That's about 75,000 square kilometers, and total metal content of about 104 million metric tons is available. So as I mentioned, the environmental impact assessment has been an integral part of the exploration program, as has been pointed out by several speakers. The environmental assessment is extremely important in order to harness these resources. This is one of the kind of typical environmental studies, which actually covers the water column, seabed, currents, and we also plans to deploy long-term and short-term moorings in the test mining site in order to assess the environment in the region. And we also have right now the best environmental baseline data for this region. Based on this, ISA has recently approved our application for the test mining, and NIOT is actively engaged in designing the deep sea mining equipment for this harnessing of these resources. So coming to the polymetallic sulfides, Professor Satish has nicely explained the origin, how the sulfides occur and emanate and create plumes, and the importance of the basic science. That's what we have done initial stages in the polymetallic sulfides exploration. We have explored the regions of Carlsberg Ridge, Central Indian Ridge, and the Southwest Indian Ridges. And on the Central Indian Ridge, we have identified the ridge segmentation and its spreading rates variability. And Carlsberg Ridge also several investigations have been done, which have indicated these two ridges belong to the slow spreading mid-ocean ridge class, and the southwestern ridge belongs to the ultra slow spreading ridge. And these geophysical investigations have given us information about the tectonic and magmatic environment of these ridges, which are crucial to locate the hydrothermal vents.
Kamesh, sorry to interrupt. Can you please wind up in a minute, please?
Yes, okay. Here, actually, we have, based on the integrated analysis of geology, geophysics, and water column studies, we identified plumes in the central Carlsberg Ridge. Two prominent fields have been identified, and we also conducted the first AEV investigations, which can dive up to 6,000 meters. This AEV is hired from the GeoMar, and we have obtained high resolution bathymetric maps about on 4 meter resolution in this region. Based on the integrated studies, here we have identified plume locations indicative of active hydrothermal vent fields. The ongoing studies, for example, now the ongoing studies based on our application to ISA are concentrated mostly on the southern segment of the Central Indian Ridge near to the Triple Junction and the Southwest Indian Ridge. Here the NCPOR is spearheading this exploration activity. We conducted multidisciplinary investigations in the region in order to delineate the zones of potential hydrothermal mineralization zones. Again, these involve studies in the water column, seabed mapping, and sampling at particular locations of interest. Like, for example, we have identified several oceanic pore complexes and recovered samples that consist of sulfide deposits. Based on these investigations, almost we have identified about 15 promising zones that could bear the hydrothermal sulfide deposits. These are the boxes allocated to us, about 100 boxes, about 10,000 square kilometers of region. Hydrothermal sulfide deposits are of three-dimensional nature, unlike the nodule area. So we have to conduct near seabed investigations with to know the three-dimensional extent of the deposits. We have used. We are proposing to use AUV at the selected location. This is the proposed track of the AUV. Each site we are proposing to cover about 50 square kilometers of region in order to completely delineate the zones of active and inactive zones of these sulfides. We propose to use the multi AUVs, multi-sensor, multi-string of AUVs to undertake this surveys, which contain subwater profiling, synthetic aperture, sonars, magnetometer, CTD, C4 imaging, and high-resolution cameras. And also we are deploying the electrical methods in order to assess the three-dimensional extent of the deposit. We are also going to use the ROVs in this exploration. And India is now acquiring its own AUV, which is capable of diving up to 6,000 meters. And now it is going to operate this AUV, and we have ROV. Now we are actually, in terms of equipment and capability, we are better off than a decade ago to conduct this deep sea mineral exploration. So at the end of this city, as looking back to the entire 40 years of our marine exploration, we have made significant contributions in the exploration of deep sea mineral resources. Yes, I agree with Professor Satish Singh. We have to couple more tightly with the basic science and address some of the outstanding questions as we embark on the deep ocean mission declared by recently by the Government of India. We are poised to take up the high resolution near seabed investigations using deep toes and AUVs and high-end geophysical tools. We also would like to deploy the ROVs in human-occupied vehicles to sample the targeted locations and conduct event-specific experiments to gain deeper insights into the mineral formation process and to study the unique ecosystems. Thank you.
Thank you very much, Kamesh. That was a comprehensive presentation on Indian efforts and which institutes in India are involved in survey and exploration of polymetallic sulfides and PM. And thank you very much for that presentation. So that ends all our presentations, all very distinguished speakers, excellent presentations in the fields that they're working on. We have a few questions. I'll try to pick a few of them. We'll try to conclude in the next few minutes, 8 minutes, maybe by 6:30. We are sorry, especially colleagues in Australia and all, it must be close to midnight. So I will actually take these questions and ask specifically to the one or two panelists. There is a question asking to clarify, is it suitable to transport gas in pipelines? Maybe Prashant, if you can quickly answer this question.
Reliance already transporting natural gas from KG Basin D6, and the natural gas being transported from Kakinada refinery to Bharuch. So it is more than I think 100 kilometers, more than that. So it's a very long distance pipeline. It is possible, yes.
Yeah, so thank you. And there is another question from Dr. Vinay. So technology answers one paradigm of the problem. And in the run-up to COP26, should we also focus on striking a finer balance between energy security and sustainable exploitation of the environment? Maybe Professor Satish Singh, would you like to take this question?
I think we are coming to the COP26 next week, so you could see that. I read an article today about Saudi Arabia and Middle East, where their economy is mainly based on oil and gas. So I think for the future, and particularly in the southern states like India, we must be very, very careful about the environment, how we exploit it. So any development must be linked to the environmental. And so it's crazy that we want to develop fast. Each country wants to do that. But I think given the climate, we must balance the two.
Thank you. Thank you very much. And we have another question.
Sorry, Srinivas, I would just add to that.
Go ahead, please.
Yeah, when we do our environmental assessments, two things. One is, of course, we have more solar potential than most countries. And that's, but that's independent of this part of our conference. But even when we look at the ocean, when we do our environmental assessments for, modules or for gas hydrates, those are the same environmental assessments that we need for wind power. And so, we should look at both as, being different parts of the coin. When we go out and do our mapping work, it's not just for exploiting the mining, but also to make sure that we can be in a good position to set up these clean energy things.
Absolutely. Absolutely. So that brings me to the next question, again to you, Hanman. So there is a question from Dr. Sudhir, who is asking how you used AUVs for applications in fisheries. Is it for data collection on environmental parameters or photographs, taking photographs of their, the fishes and their ecosystems? So this is a question to you.
Yeah, so, there's a big paradigm shift in fisheries where typically how they manage fisheries is by actually going out and catching them and seeing how many fish they can catch. But the fisheries are so exploited that catching them doesn't make sense. A simple way of thinking about this is can we take a robot and get pictures of fish and then count them from that? And that's what we're trying to do. But there are all these complications. For instance, some fish try to avoid a vehicle. Other fish are attracted to it. And so we need to understand all these interactions. And so it's a long-term program. And, NOAA is very interested in this. And it has been funding it for over 20 years. That is what we're trying to do. We're trying to see how can we count all the fish in the world's oceans without disturbing them and without catching them.
Perfect. Thank you. And we have another question. This is from Maria Fraser from Guyana. So she's thanking all the presenters for their excellent presentations. And so she's asking if the presentations could be made available. I'm sure you wouldn't mind if these presentations are shared with the participants. And if that is the case, I will actually work with the organizers. I'll work with Ankita to ensure these presentations are made available by hosting them on a website at MEA or at INCOIS. So I'm sure we will work on those aspects, Maria. So that's all from the questions. And is any final words from any panelist on any of these questions? Yes, please go ahead, Satish.
Yes. One thing it is not clear to me where you are going. What was the purpose of this meeting? Are you going to do something with this whole presentations, the idea you brought us together? But it would be a good idea to think how to use this, our communication contacts or the science or technology for the future of India. I think we need something on that.
Yes. So, yes, go ahead. Go ahead, Krishna.
Thanks. I think Professor Satish has pointed a very interesting thing, and this is something which all diaspora out of India have been looking for. Few years. And I think we need to have some follow-up meetings if we can organize in this way based on this conference and presentations if shared with Indian scientific community, industries. Maybe there could be some summit with industries, academia in India as well as abroad, and then chalk out some strategy. I think that integration, that networking is important rather than just having events. I think that's what Professor Satish is pointing out. Maybe I said more loudly. One comment I wanted to pass on the question that was asked to me. was about transportation of gas. I mean, I only specified about natural gas, but CO2 transportation has been really big business, has been operational, and it has been in practice with in US fields. From source it is captured and transported to oil reservoirs for CO2 or operations. But at the same time, CO2 transport is becoming more lucrative for underground storage in UKC's region or Norwegian region, European area. At the same time, we are also looking for hydrogen transportation in pipeline, which is a byproduct from flue gas if separation facilities such as St. Ferguson Akan project, and then I'm proposing my projects to transport hydrogen as well as CO2. And here, hydrogen can be transported to the national grid that works on the electricity generation. So wind turbines converts electricity from wind turbines can be converted to hydrogen, stored underground, and can be produced for mitigating demand. But this is again based on local demand, India's overall energy supply, etc. So hydrogen, CO2, natural gas transportation through pipeline is all feasible, but it needs a lot of investment. Pipeline material, etc., is very important aspects of those.
Yes, yes. Thank you, Prashant. Thank you for making those important points. Yes, Shyam, please go ahead.
Yeah, it is good that we have had a chance of speak to the minister or the panelists, and I think this is a way forward, and maybe they should continue, and maybe a proper arrangement should be made to speak to each other and made the message available to the industry and different institutions in India. Because, for example, we had an Indo-Norwegian program collaborating with some institutes in India on joint project with where Norwegian government was funded for 4 or 5 years called PSET, and then it just died out because there was not much response from both the governments. So maybe there should be a effort from the government level also to make it happen, so that we will support in all the way.
Thank you.
To follow up on that, I hate to say it, but and this is not only an Indian problem. Whenever we go to international collaborations, we always go to these conferences, we talk about it, and the reality is, in 90% of the time, nothing happens. Okay, I'll be very honest. But what we've learned over the last 20, 25 years is we should not think about starting with $10 million projects. Let's start very simply. Can we just do a simple student exchange? Send students from India who are grad students to our universities all over the place. That's low-hanging fruit. It builds these relationships. And then what happens when these students come is we have joint publications because they're working with people in India, and then that builds that trust. And then, you don't hesitate to pick up the phone and call me and say, Hanu, we want to do this. Can we do this? And when I know somebody, then I will react very differently than if I get a cold call from someone I do not know. And so I think we should start small. I think we should build up to it, but I'm hoping we don't go to the point where, we all love each other. These are great presentations and nothing comes out of them.
Yeah. Yes, Satish, final word from you, and then I will give my concluding remarks and go over to also Ms. Manika Jain for her, final remarks.
We are talking to the ministers.
Yes, please.
And so here is the real decision-making people we are communicating with. So we have been talking about all these programs for a very long time. And the message I am passing, and every time I talk to India, is that talking is important. But I think a big long-term program in any area you choose, the way that you did for gas hydrate. In other areas, as you said, that only country has an ocean named is India. And we are far behind understanding of the Indian Ocean. Others have done a lot more than we had done. So I think I gave a talk a couple of months ago. I said the same thing, that we should have a big Indian ocean program focused on getting right people. Other thing which is missing in India is getting right people to be involved in and providing the leadership, which is missing. So Chinese had done a very good job at bringing Chinese from West, giving them the positions, working with them and boosting. Look at the research today in China. It is all the Chinese coming from outside who has provided the input, so much input, that the China's standard, both scientifically, is much higher today. And even the US is worried about. And I think India should take the same ambition and try to push it, because as you said, that Indians abroad are as bright as anyone else. But we are not able to put that energy. In IT, we did it, but not in any other area. Maybe space, we had done it. But in the whole area of ocean science, let's say, we have not done it. Take advantage of these resources. Hanumant, you are the expert on the submersible. And you should be there advising NOIT on this and helping them. No, nothing. Same story with everything else. I've been working in marine science for the last 30 years. I had a zero project formally with India. I work with Kamesh Raju because we are friends. But trying to build up really program, taking advantage of that is missing. And going big way is the only way to go forward.
All right. Thank you very much for all those very useful comments made by the panelists in the end. In fact, your presentations were excellent. Thank you very much for we could pick up leads from each of your talks and then link them to initiatives that we are doing in India. And then your strong message that we get at the end is how do we work on the follow-up of what we have done now? I think that's a very important point. We will take it back. And then whether we should have a group, whether we need to plan a follow-on summit, how do we sustain links with with the Indian scientists formally, and then with your institutions back in the countries where you are working, with the Indian institutions. I think that's that forward-looking kind of institutional mechanism is, I think, what you're proposing, student exchange, which Hanumant mentioned, Satish, I think all of you, I think that was the point that you were trying to make. I think that is something which we will certainly put in our, recommendations and then come up with some kind of a plan. And in conclusion, trying to sum up what we spoke, I'm actually going backwards. I spoke about the last issue that we discussed, and then going backwards. And then I think you all made excellent points about the basic science on marine resources, both living and non-living. We need to all our exploitation, exploration, production, everything should be built on a bedrock of basic science. So that is something which we will take note. And then we've also spoke about all kinds of energies, starting right from gas hydrates to polymetallic sulfides to all that So, and also on the impact of exploitation on marine benthic ecosystems or marine ecosystems in general. And then Sashi made a good presentation on the opportunities in in productionizing the seagrasses and other such coastal keystone species. So again, technologies across all these topics that we have discussed. We've heard about how technologies can be helpful, the AUVs, ROVs, and so on and so forth. And then bringing students into the entire equation, it changes the whole, game. So that is something which is very important. We will take those on board. And coming a bit about Indian laboratories, we had Kamesh spoke about them. You all have been working in some form or the other, formally or informally, with some of the laboratories. But I would like to just mention that under the Ministry of Earth Sciences, which is one of the co-sponsor of this event, there are several laboratories like NCPOR, who has been working a very big way on polymetallic sulfides, and NIOT, which Satish mentioned, the National Institute of Ocean Technology, working on AUVs, ROVs, and those kind of technologies, deep sea mining vehicles, human submersibles. All those things are being worked on. So it's very good to link them with the work that you are doing. And even outside MOEs, of course, we also have an institute called CMLRE, if you have heard about it. which works on marine living resources, works on marine biodiversity, so on and so forth. Outside MOES, again, we have institutes like CSR, NIO, NGRI, and several other institutes. GSI has a marine division which work on all these technologies and resource exploration and mapping that we are talking about. And of course, there is industry. You all have worked with industry, ONGC, etc. Now, what is the way going forward? You all asked about the institutional mechanism and what is India doing big. I think the Deep Ocean mission that has been recently launched by the government, it's a very high profile mission. It is bringing together a lot of these components that we have been doing in different places, bringing them together under one big umbrella, providing a fantastic framework for collaborations within the country, within institutes, among institutes within the country, and also open up opportunities for external collaborations. So that is something I think we will keep, sensitizing all of you on, share information on. And then, of course, there are other collaborative bilateral programs that India is doing through the kind support of, great support of MEE. So we have, like, for example, say, India-US joint collaborative framework. We have an umbrella framework under which India and US maintains Rama buoys, mood buoys. Very successful program. We are now expanding it to actually doing a big program in the Arabian Sea for, monsoon forecasting kind of applications, ocean modeling applications. So there are bilaterals with several countries. I'm sure Madam Manika will add a bit more information on that. So what I'm trying to say is there are frameworks. We need to explore the right kind of framework with the right kind of experts. So that is something, and we will try to continue working on those lines. So I will conclude here and then thank all of you once again for your wonderful presentations and the discourse. I would like to thank Ms. Manika Jain, Honorable Minister for State for External Affairs, and also my colleagues, Dr. Parvinder Maini, who is sitting through this session, and Dr. Ramdas, who is the Director of NIOT, who has been indisposed, and I had to replace him actually in the last minute. So I thank each and every one of you and hand over back to Madam Manika Jain.
Thank you for your, of course, excellent conclusion to the excellent and very valuable, I would say, inspiring presentations. The point which I wanted to, which you have made in the end, some of the speakers, the panelists, I would say in my opening remarks, I had already kind of said that the whole purpose of this conference, or you can say, or this interaction, is not to leave it here or run off or whatever. And our basic idea is to have various forums where we can interact with Indian diaspora, and this being one, a special forum where the nodal, as you said, the nodal government agency is Ministry of Earth Sciences, and I'm sure they're going to come out with not only a report on this presentation, they'll put up these presentations up on the public, either website or even, I think so, if you can bring it out in print also, whatever that would be, I think so lovely for everybody to see it and share it. And also we think that your recommendations will be taken very seriously with Ministry of Earth Sciences, and we'll then see what follow-up can be done. And of course, ME is always there to kind of help bridging that gap of people who are sitting abroad, and whatever is happening in India there, we facilitate, bringing them all together on one platform. So with these words, I think so I'll thank you all, and we look forward to an outcome of this conference very soon, which will be shared with you, and of course with the other stakeholders, out in India. Thank you so much for being with us and sparing your valuable time and giving your valuable inputs. Over to Ankita.
Thank you, ma'am. With this, we conclude the conference. I thank everyone, all the panelists and audience who have stayed with us, and I wish you all a very happy weekend.
Thank you.
When you ask to come to Paris, you will be welcome.
Very much. Thank you.
Thank you, everyone.
Bye-bye.
Okay, bye-bye.
Srinivas, sir, thank you very much. Thank you.
Thank you. Thank you very much.